Greetings everyone, Apoorv here. In this video, I am going to be introducing you to this exciting world of theory of computation and start off with the applications of CFG, that is, context-free grammar in speech recognition. To give a bit background on myself, I am a sophomore from the Department of Computer Science and Energy. So before we begin, I hope to break down this complex concept of CFG and its application in speech recognition. So without further ado, let's dive into this. As Wendell Berry said, we live beyond words as also we lived beyond computation and beyond theory. Words, computation, and theory are being used to make advancements in speech recognition technology. Through this presentation, we'll be taking a tour through what exactly is theory of computation, the meaning of context-free grammar with respect to the same, and its application in speech recognition. So, what exactly is TOC or theory of computation? Theory of computation is a branch of computer science and mathematics combined that deals with how efficiently problems can be solved on a model of computation using an algorithm. It studies the general properties of computation, which in turn helps increase the efficiency at which computers solve problems. This is done when we estimate the validity of the solutions given by the computer through the theory of computation and then alternate the algorithms so that we can obtain a more reliable solution. This is a fast growing branch that has helped solving problems in many fields beside computer science such as physics, economics, biology, and many more. So, this branch was actually established around 20th century by the mathematicians. This branch includes of three sub theories, which are automata theory, computability theory, and complexity theory. Automata theory is the study of abstract machines and automata as well as the computational problems that can be solved using the same. The most powerful model of automata is the Turing machine. Computability theory is when we are able to formulate the problem using Turing machine easily, but we can never be able to solve it. In other words, it is when the computer is able to address the problem but unable to come up with the solution for the same. Computational complexity theory. The complexity theory discusses the efficiency at which a problem could be solved. This is done by considering two major aspects, time complexity as well as space complexity, which are the measures of the number of steps needed to analyze and solve the problem, and thus determining the memory space needed to solve the problem. In order to predetermine the space and time that will be needed, computer scientists link these two factors to the amount of input that will be received, as the time and space needed increase linearly as the amount of input increases. So, what exactly is context-free grammar? A context-free grammar is a formal grammar which is used to generate all the possible patterns of strings in a formal language. So, coming to this very diagram of two derivations. So these are basically the derivation trees for one single expression, which is x plus y into z, and coming to this next diagram, which also conveys the same, is nothing but x plus y into z. So these are just two different ways of representing the same expression. Now, a context-free grammar has four components. A set of terminal symbols, which are the characters of the alphabet that appear in the strings generated by the grammar. A set of non-terminals, which are placeholders for patterns of terminal symbols that can be generated by a non-terminal symbol. A set of production, which are rules for replacing or rewriting non-terminal symbols, which are on the left side of the production in a string, with other non-terminal or terminal symbols, which are on the right side of the production. And then a start symbol, which is a special non-terminal symbol that appears in the initial string generated by the grammar. Next, speech recognition. I'm pretty sure this term is a very famous one, ranging right from escaping the urge of typing an assignment to recording important concepts during a meet textually. Speech recognition is already a part of our everyday lives, but for now is still limited to relatively simple commands. As the technology advances, researchers will be able to create more intelligent systems that understand conversational speech. Given current trends, speech recognition technology will be a fast growing and world changing subset of the signal processing for years to come. Speech recognition system uses computer algorithms to process and interpret spoken words and convert them into text. They must adapt to the highly variable and context specific nature of human languages. Various algorithms as well as computation techniques are being used to recognize the same, namely natural language processing, hidden Markov models, engrams, and neural networks. So why exactly speech recognition? What is the motive behind the same? So to understand the same, we must first understand what is the task and why is it so. Getting a computer to understand the spoken language is the task. But what do we mean by understand the spoken language? By understand the spoken language, we mean that react appropriate to the same and convert the input speech into another medium, whether it's, for example, text over here. So how do we humans do it? We humans, as you see in the diagram, the speech is being released out by the human, which is then traverses through the three medium and then goes to our ears, which are then sensed by the ears and are thus interpreted by the brain. So here we have not so complex examples stating how machines recognize the basic human speech consisting of acoustic analysis of the speech signal. So how might computers do it? Digitization. Yes, you heard it right. Digitization is the solution to all. Acoustic analysis of the speech signal and then finally the linguistic interpretation of the same. So, what exactly is so hard about it? Now, let's first look upon the challenges and will then understand the same through a couple of examples. So, digitization, converting analog signal into digital representation. Signal processing, which is separating speech from background noises. Phonetics, which is variability in human speech. Phonology, recognizing individual sound distinctions. Lexicology and syntax, disambiguating homophones. Syntax and pragmatics, interpreting prosodic features. Pragmatics, filtering of performance errors. So let's now come to the example which I had previously talked about. So here as we take the word code, which can be broken down into K, O and T, but then it can be interpreted as KOWT, which is a bit different from the actual version of our human speech. So for example, if a human says recognize speech, so here there are chances that the computer might take it as recognize speech, which is nowhere near to the actual meaning. So let's come to HMMs. What exactly is HMM? A hidden Markov model is a computer tool that tries to guess what might happen next based on the patterns and its dues it has seen before. Even if it doesn't have all the information it needs to be sure. It is basically like playing I Spy with a computer, where the computer has to make a guess about what you're thinking of based on the clues you give, but sometimes it doesn't have all the clues it needs to be completely sure of. So here let's discuss each and every model here. So the word model for the word the. These decimals are the probabilities of choosing the respective paths. As you have seen the automata diagrams, the models, these are the same. So here for the word model, it will first be taking the pronunciation the and then ax. So starting from this, it comes to the end and it will thus be able to process the word the. For the word on, it first comes to a, which is the strong form of a, and then na, which combinedly becomes on. And then we have the word model need. Need by few people can be told as N, I, and D, which is basically need. Else, few people stop it with ni. So that is how the computer should process it. These are the probabilities corresponding to the same. And then coming to the letter I or referring to the person I, these are the probabilities. People may take it as I, or few take it as the singular pronunciation, which is I, which is the slower version of the same. So, the best way out. What do you think is the best way out to figure out the speech to text? Okay, let me tell the same. Analyze training data in terms of relevant features. What exactly do we mean by analyzing training features in terms of relevant features? Here we take in data sets and then train them using the machine learning models for better enhancements in the same. Learn from large amount of data and having different possibilities. And then finally combine these into hidden Markov model expressing the probabilities for higher efficiencies. Voice recognition. So here we have a diagram which will show us the pathway from which a human voice is converted into a text. So here as you can see the voice is transferred and then it has gone to the system module wherein we have the speech enhancer and then gone to the feature extraction and then we give it to a testing module for feature matching then train the same in case of future references using the speaker modeling. It is then saved into the speaker's database, and then we have the decision, and finally we have our text ready. And here we have this text to speech to text flow. So speech recognition can be divided into the following. The starting from the very beginning, which is acoustic or sound wave, which is the normal human speech. So this is converted into frequency spectrum using filtering, sampling, spectral analysis, and FFT. And then the frequency spectrum waves can then be converted into features or phenoms for the meaning the context using signal processing and analysis. Phenom recognition, HMM, and neural networks are used for converting the same into phenoms, and phenom sequences of words can be done using grammar or basic statistics, which might be complex at times. And then the same is converted using higher advanced statistics into word sequences or sentences, which are basically our text. Coming to the role of the context-free grammar over here. This context is based on the Berkeley Restaurant Project with medium vocabulary of 1300 words. A Viterbi decoder uses the Viterbi algorithm for decoding a bit stream that has been encoded using a convolutional code and tells the code. SCFG as a language model improves word error rate from 34.6 to 29.6 and semantic sentence recognition error from 39 to 34.6%. In addition to the same, it can further reduce it to 28.8 word error by mixing the bigram and SCFG elements. A number of researchers have proposed ways to use natural language. BERP consists of the feature extractor, a multi-layer perceptron, phonetic probability estimator, a Viterbi decoder, an H&M lexicon, a natural language interpreter which incorporates a stochastic context-free grammar, and a database of restaurants. The SCFG used in BERP consists of 1389 handwritten context-free rules. The non-terminals in the rules are very specific to the corpus and hence encode semantic information particular to the restaurant domain. The rule probabilities are learned from the 4786 sentence BERP corpus along with the EM algorithm. Here, the figure shows the sample of grammar rules with the probabilities for each. So now, many developments have been made on usage of context-free grammar in speech recognition for the past few years, and many experiments are being conducted to make significant improvements in the same. Advancement in the field allows speech recognition to be faster and more accurate. In conclusion, we have explored the fascinating applications of context-free grammar in speech recognition. We learned how powerful this tool is and can be used to improve accuracy and efficiency in natural language processing. I hope you found this video informative and useful. Thank you for watching the same.